All right. All right, cool. All right, let's get started. Welcome to another installment of Universe at Home, brought to you by the Minnesota Institute of Astrophysics. So Universe at Home is basically a web series hosted by us students, where the whole purpose is that we want to give you a peek behind that astrophysics curtain. So this week, we're going to be talking about Hubble, the Extraterrestrial Observatory. My name is Josh Mays, and I'm currently a junior here studying aerospace engineering. And I also have the honor of being joined by two fellow space fanatics.
Hi, my name is Avery Wold. I'm a fourth year physics and astrophysics student here at the U. Yeah.
And my name is Nico Adams. I'm a third year PhD student studying astrophysics and focusing on star-forming galaxies. The basic outline of tonight is that I'll be giving the main talk for about 20 to 25 minutes at the beginning. So that'll give you sort of an overview of the history of Hubble from hopefully some perspectives that you haven't seen before, because I had a lot of fun putting this together and learning about just how crazy it was that we have the Hubble floating in space right now. And appreciate that a lot more deeply myself, and hopefully we'll get you to appreciate it more deeply as well. I'm sure everyone in this chat has at least heard the name Hubble telescope before, even if you don't know a whole lot or certainly everything about it. The structure of tonight is I'll start with the talk, and then as that's going, feel free to leave us questions in the chat. Just type them up, and our moderator, Josh, will be watching it and will raise them at the end of the talk. Or if they're really pressing, he can raise them right away. And it doesn't have to be about the talk. It can be general questions about space are perfectly welcome. We are here as your astrophysics fanatics is actually a good word for it. So with that said, let's get started and we can go from there. So the title of tonight's talk is Hubble, the Extraterrestrial Observatory. And I turned that over in my head for a bit. I wanted to give a talk about what Hubble was. And in the end, I settled on that name because the coolest thing about Hubble is that it's currently in space. And I'm going to go into a lot more detail about why that is so crazy. By the numbers, just to give you an idea of what Hubble is. Hubble is a space telescope. It was launched in 1990. And as of April 2020, it has been orbiting around the Earth in low Earth orbit for 30 years. So in that time, it has taken over 1.4 million observations. And it, just for fun, you can note that it weighs about 24,000 pounds, and it is usually said to be about the size of a school bus. In terms of the total cost to put it in orbit, to build it and put it in orbit, it took about $5 billion of NASA funding. And to put that in perspective, if you take that weight and divide it, if you take that cost and divide it by that weight, you end up with $12,000 per ounce, which I went and compared to the price of gold. And as it turns out, if you had sculpted the Hubble telescope pound for pound out of gold and just put it on the ground, it would have been 10 times cheaper to build it that way than it was to actually create the telescope that we currently have in orbit and put it into orbit. So this was a huge investment. This was not something, this was not like a minor program. This is one of NASA's largest endeavors of the last 30 years. So I want to go into detail about why we needed a telescope in space. And in order to do that, I need to talk about why we want how telescopes usually work on the ground. And you can't really talk about telescopes without talking about observatories. So I'm going to start with an observatory. Hopefully many of you are tuning in from the Midwest, where this program is based, at the University of Minnesota. So I'm going to talk about the Yerkes Observatory, which from 1900 to 1950 was considered one of the foremost observatories in the world. This is what it looks like. From end to end, it's about a football field in length. So you can actually compare that to the size of the Hubble telescope, zooming in to sit on the lawn. And it does not compare at all. The Hubble is much, much, much more compact than what you see here. So what are you using all of this space for? Why do you need all of this entire building to host just a couple of telescopes? So what makes an observatory is, first, you need a telescope. That telescope, in Yerkes' case, is a gigantic sort of behemoth of a tube sitting on top of a plinth. And that plinth is called the mount. In this case, it's an equatorial mount that is designed to rotate in the same way that the Earth rotates. So you can easily turn this telescope to counteract the rotation of the Earth. On top of the telescope, you need a very advanced set of controls that can actually point the telescope and get it to be extremely precise. So the Yerkes telescope and most telescopes of its era could be calibrated to 1,000th of a degree on the sky to see things as precisely as it did. On top of that, you needed somewhere to actually store the observations that you were making. So for most of history, observatories included places to develop and store photographic plates. This is less important today because we have digital photography. And so if you're putting something into a telescope, it's usually not a photographic plate. It's usually a camera. And that camera can store things on a hard drive. But for most of history, when the Hubble was being proposed and built, this is how astronomy was done, is that you actually had to take a photographic plate, put it in a dark room, and develop it. And that was the only way that you could store the images that you were taking. So there were giant storage facilities for these things at many observatories. And here's an astronomer showing a filing system for some of them. And finally, in order to keep all of this running smoothly, you needed a crew that could actually maintain it. So you needed to do maintenance. Observatories throughout history were known for having crews of full-time telescope operators and specialists, oftentimes people who would live in these remote mountaintop areas, and whose only job it was to take directions from astronomers who needed to point the telescope and make sure everything was running smoothly, and also make sure that it was in peak shape for observations that happened every single night that there was good weather. So to sum up, an observatory is a telescope and also controls for the telescope and an array of specialized tools that you might want to put into the telescope, and a dome to house the telescope, and also astronomers who need to be able to access the observatory in order to direct observations, and also telescope specialists who can help the astronomers and take care of the telescope, and housing for all of these people on site so that they can be so that they can sleep during the day and make their night journeys to the telescope to do their work, and also places to store and develop all the observations that these people are taking. And the list keeps going on and on and on. I spent so long describing this because I want you to keep in mind that what people were proposing with the Hubble telescope is in 1940, in the 1940s, when the idea of a space telescope was first floated, an astronomer basically went to other people and said, hey, let's take an entire observatory, like the Yerkes is pictured here, put it onto a rocket, and launch it into space. So all that list of things that you just saw on the previous slide somehow has to work when the telescope and everything that is attached to the telescope is in orbit, and all of the human beings, for the most part, are not. And that was a gigantic challenge. So that brings us to part two. Why did we actually need an observatory in space at all? So the original proposal for the Hubble telescope happened in 1946. And it was from an astronomer named Lyman Spitzer, who now actually has a space telescope named after him called the Spitzer Space Telescope. He did not get the title of Hubble, but he is considered to be the father of the Hubble telescope. So in his proposal, a line that sums up his position really well is, such a scientific tool, if practically feasible, could revolutionize astronomical techniques and open up completely new vistas of astronomical research. And this is from his essay, Astronomical Advantages of an Extraterrestrial Observatory. So remember, in 1946, we did not have rocketry. We could not send things into space yet. So this was a very theoretical paper, but his argument basically rested on two major things that a space telescope could do that a ground-based telescope could not. The first thing has to do with frequency. So as most of you know, visible light spans from red light, which is the lowest energy frequency the human eye can see, to blue light, which is the highest energy. You might have heard red to purple, and there's a lot of complexity with how human beings actually see those colors. But the idea is that we can only see three colors with our eyes: red, green, and blue, and combinations of them make every color we see. However, the spectrum of visible light is only a tiny part of the spectrum of all light that can be emitted by objects. It goes all the way down to gamma rays in the highest energy direction and radio waves in the lowest energy direction. So just looking into telescopes with our eyes was never going to be enough. Astronomers, if they really wanted to understand the universe, needed to look at all of these other frequencies because they all tell us different things about basically space, things and the things that are in it. The really unfortunate part about living on Earth, for telescopes, the really fortunate part for human beings is that most radiation from space is completely blocked by the atmosphere. So this diagram is a fun way of illustrating that. On the left, you have high energy radiation, and it goes by wavelength, which has to do with the size of the wave that is carrying that radiation. And anything that is higher energy than what we can see, as it turns out, is almost completely blocked by the atmosphere. This is excellent. If you've ever gotten a sunburn, it would be imagine that, but far, 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 far worse if the atmosphere was not doing this for you. Higher energy radiation has carries a lot of danger for human beings, but it carries a lot of information for telescopes as well. And it's almost completely blocked. Very little of it can get through the atmosphere down to telescopes on the ground. On top of that, we get this really nice window for visible light, but then things are a little iffier for the infrared spectrum, for microwaves, and for radio waves, which are all forms of radiation that we are astronomically interested in. So when we look at the spectrum of infrared light, there's this huge part in brown that is almost completely blocked or completely blocked by the atmosphere. And it contains a lot of interesting information that we just can't see on the ground. So effectively, by taking observations from the ground, we are taking all of these different views of galaxies. These are real pictures, by the way, assembled of a single galaxy that we now know this is what they look like from telescopes that we have in space. From the ground, the only versions of this galaxy that we would be able to see are the radio and the visible. So we are limiting ourselves to a really tiny fraction of the information that we can get astronomically by taking observations on the ground. So the second reason, unrelated to frequency, is in space, we get much better telescope resolution than we can on the ground. And this is for a pretty simple reason, which is that random motions in the air of our atmosphere cause images from space to become blurry. So this is what's known as astronomical seeing. And we're looking for a good image to represent this. This is a pair of observations from a high-quality telescope on 2 different days. And on one of them, the air was blurry, and on the other one, the air was clear. This has a lot to do with the weather. So if there's a lot of water in the atmosphere, or if there's a lot of heat or a lot of turbulence, essentially you'll just get light that bounces off of the air a little bit more before it reaches the telescope. As opposed to on days where you have clearer air, you typically get images that are much sharper. So this is why most observatories are placed on mountaintops, because even getting above a little bit of the air in the atmosphere and that much closer to space makes all of the difference for ground-based telescopes. This is such a huge problem that places on the Earth with good seeing are these highly prized locations for astronomy. So if you ever heard of an observatory in Chile, it's because a huge number of them are in the Chilean Andes Mountains, just to avoid this effect. So to give you an idea of how significant this is, I took a galaxy and I showed you what you could see of it in a typical backyard telescope. So this is what you would get if you had like an 8-inch aperture. You're limited in this case by the size of the telescope. It just can't collect enough. Its aperture is not large enough to give you a clearer view than this. On the other hand, something as large as the Yerkes telescope, or our current best ground-based telescopes, can see this galaxy as well as this. You can make them large enough so that you can collect a lot more information and get a much higher resolution view of the galaxy. And this is where it stops. You actually cannot see this particular galaxy, NGC 4038, any better than this from the ground. On a clear night, this is about the best you can get. So compare that to what you can get if you completely remove the atmosphere and have no air in the way. And this is the actual image that the Hubble telescope eventually took. This is the actual image that the Hubble telescope actually took. So the idea is that for a telescope on the ground, you are limited by seeing. You're limited by the amount of that the air blurs your image. And in space, you're only limited by the size of your telescope. And that is called the diffraction limit. As your telescope gets larger, diffraction effects of light within it, bending of light around corners essentially, becomes less and less important, and you get clearer and clearer images. So however large a telescope we want to put into space, that is how good our image is going to be. So to really drive this home, by the way, I'm going to focus one more time on just this patch of stars, just these stellar clusters. This is the best view that we can get from them from Earth, and this is the view that we actually got from the Hubble telescope. So it's a really significant effect. So all of this is to justify why we needed a space telescope. To actually get Hubble into space was a very different endeavor. And there are a lot of stories that are often told about this. I'm unfortunately going to skip over a lot of those because I think the really interesting part of Hubble's history is not how it specifically got into space, but how the idea of a space telescope was totally different than anything that came before it. So in 1968, a proposal was floated in NASA for a large space telescope. And it basically looked like this. You can see from this diagram that there were going to be some solar panels that were going to give it energy connected to a bank of batteries inside. And there was going to be this sort of round tube that stored all of Hubble's instruments, all of its mirrors, and everything that it needed to record the data that it took. Then there were going to be these antennae that were going to transmit that data to Earth. And about 22 years later, we actually launched the telescope that looked very much like that. You can compare these two and see that they're very similar. So we had to answer a couple of major questions about how this is going to work, because remember, we couldn't take most of what an observatory was with us into space. So the first question was, how do you actually point a space telescope? On the ground, it's very easy. You just put a bunch of knobs on it. So you can basically put the controls right on the telescope and make them as precise as you want. In space, you have to do everything remotely. And so what ended up happening is since we don't have a ground for the Hubble to stabilize itself against, we have to use gyroscopes. A gyroscope, if you've ever played with it, in its simplest form, a lot of us know it as just what happens if you spin a top. As soon as that top starts spinning, it does not want to tip over. It sort of self-stabilizes. And taken to an extreme, you can make devices that are spinning that are so extremely precise and resist turning so much that you can tell if it has turned at all by measuring it to a fraction of a degree. And that is exactly how Hubble's gyroscopes work. Essentially, they put 6 gyroscopes on Hubble, 3, as I understand it, in the fine guidance sensors, and 3 in these dedicated gyroscope storage containers down here. And those 6 gyroscopes tell Hubble how it's pointed, so that if an astronomer ever says, hey, I want you to point at this very specific spot in this very specific part of the sky to within a 10th or a 100th of a degree, Hubble can actually do it. It can run its motors, rotate itself, and then stop at exactly that point. So that's how we solved the problem of rotation. Another really serious problem is how Hubble was actually going to get its observations down to us. Because remember, Hubble was coming off of the era of photographic plate photography. Digital photography was still very new when Hubble was being proposed. It really hadn't come into fruition yet. So for the most part, astronomers on the ground were actually taking physical photographic plates, loading them into their telescopes, taking them out, developing them in dark rooms, and then very carefully storing them so that they did not get damaged. And the only way that Hubble could do that is if it somehow launched those photographic plates down to Earth. It was just not going to work. So instead, what happened is Hubble was given an onboard storage system and some very powerful antennae. And what you see here is known as the low gain antenna and the high gain antenna, small and big, basically. And between those two, Hubble is able to transmit each observation that it takes down to Earth pretty efficiently. It actually transmits about a terabyte per month, as I understand it, which for 1990, remember the internet did not exist at the time that the Hubble telescope originally launched. So transmitting a terabyte of data per month over a satellite network was challenging. It was not an easy thing to do. Finally, there's a very valid question that you might ask, which is, what if something goes wrong on the Hubble telescope and it needs to be fixed or maintained or needs a replacement part? Again, you can see an image of that in sort of the classical version of astronomy for ground-based telescopes. You would just take the part off, polish it, or do what you needed to do, and then put it back on. In space, you cannot do that easily. But things do go wrong, especially in space, because there are a lot of hazards in space, and there's a lot of challenge in getting a telescope into orbit in the first place. So as many of you may know, Hubble actually launched with a very significant flaw, which is its gigantic mirror, which is about 6 feet across, had a tiny flaw in it where it was ground a little bit too finely on the edges. And the result of that is that images of space were not nearly as sharp as they were supposed to be. We went from images that were supposed to look like this to images that actually looked like this. And the flaw in the mirror was only about the size of what's usually said is 1/50th of a human hair, or about 1 micrometer. So this tiny flaw almost completely ruined the optics of the telescope. The only way that people could figure out how to fix it was to install corrective optics onto the telescope. So in essence, adding new parts to redirect the light slightly to correct this problem, since it was very well understood as a flaw. So there's only one way to do that. You actually have to send a person to maintain the telescope. And that is why we've had the Hubble servicing missions over the years. So between 1993 and 2009, we've actually been back up to the Hubble Space Telescope as humanity 4 times by sending crews up to rendezvous with it and basically perform the equivalent of brain surgery in orbit. These people had to be really careful not to touch the gyroscopes or the other important tools on Hubble because they did not have replacement parts for them. And had they disturbed them, the gyroscopes would have been useless effectively. So this is a picture of someone actually installing the corrective optics that fixed Hubble's primary mirror issue. And from that moment on, Hubble was fully functioning, and it became one of the most desirable telescopes in the world. So to wrap up, I want to spend a few minutes talking about what Hubble has actually shown us. So we've invested all of this time, we've invested all of this money. What have we actually gotten out of it? What has Hubble taught us new about the universe? And to give this some context, I'm going to start close to home and then gradually zoom out a little bit. During the activity at the end of tonight, by the way, we'll show a lot more images of things that the Hubble has photographed. But for now, I'm just going to focus on a couple of major findings at lots of different levels of distance from us. So we can start very close to home at our next door neighbor, Mars. In 1990, in the very early 90s, even before its corrective optics were installed, so Hubble was still a very blurry telescope, it still got the sharpest view of Mars that we had ever gotten. And that actually meant that we discovered new elements that we did not expect in the atmosphere of Mars for the first time. Scientists were able to confirm that ozone was present in Mars and was able to confirm that there were sort of cloud-like structures in the atmosphere that they had not seen before. Zooming out a little bit more, we reached Jupiter. And one of the exciting things about our images of Jupiter is that Hubble was one of the first ultraviolet telescopes. So essentially, it was the only telescope around that could see into the ultraviolet part of the electromagnetic spectrum that wasn't blocked by the atmosphere. And all of a sudden, we could look at Jupiter in ultraviolet and see its aurora borealis, effectively, but for Jupiter. And we got a much better idea of what that looked like. So this is a picture of the ultraviolet of the aurora superimposed on a normal visual image, optical image of Jupiter. One of the really cool stories that came out of Hubble is, oh shoot, that circle's a little bit off center, but around 1994, right after the corrective optics were installed into Hubble, Jupiter actually got hit by a comet known as the Schumacher-Levy comet, I believe. And you can see in the lower left corner of this picture of Jupiter, there's this tiny flash that didn't used to be there, which suddenly expands hugely and then subsides. So this is 4 pictures of a gigantic impact happening on Jupiter. And Hubble was one of the first telescopes to capture that, and certainly the best telescope to capture that. It caught sharper images of this than any other telescope in the world, and sort of became world-renowned for the first time. This was sort of the Comet Neowise of its day. For those who remember the Comet Neowise of the summer, it became a really popular phenomenon that everyone was aware of. So zooming out a little bit more, we get to Pluto. One of the things I found out while preparing this talk, Hubble actually discovered 4 new moons of Pluto. It had a sharp enough eye and could collect enough light that it actually noticed 4 points of light around Pluto and was able to plot out exactly what their orbits looked like, which are these 4 rings. So they are much smaller than Charon and reflect a lot less light, which is why you see a blue screen here and a very black image here. These are long exposure photographs on the sides versus a very short exposure in the middle, because there is simply so much light coming from Pluto and Charon that this image would not work if you had a long an exposure of the same length, of the same amount of time in the center. So this is a combined image to show just how faint these points of light are, but to still make them stand out in a way that you can compare. So this was really exciting. We did not expect there to be such a complicated system of moons around such a small, what is now known as a dwarf planet. So zooming out even further, Hubble was one of the first telescopes to offer a sharp view of stars forming in real time. And one of the best pictures of that was the Orion Nebula. So this is something that you can actually see with the naked eye on a dark enough night. It's part of the constellation Orion. And it's sort of between the legs of the constellation, if you know where to look. So Hubble was the telescope that offered the sharpest picture of this, and essentially picked out all of these new stars that we did not expect to find because they were obscured in optical wavelengths, but we could see them in infrared and in other wavelengths as well. So after this point, we leave the galaxy and we can look out into our nearest neighbor galaxy called the Large Magellanic Cloud. And one of the things that the Large Magellanic Cloud is famous for is in 1987, a supernova actually exploded there and was very briefly visible to the naked eye on Earth. We now study the remnants of that, and Hubble was one of the first telescopes that could resolve the individual stars in our nearest neighbor galaxy instead of just seeing it as one giant cloud. So it could zoom in sharply enough that it can actually see the fine substructures that make up the remnants of that supernova. And to wrap up, we're going to go basically as big as possible. We can see galaxies much more sharply than we ever could before. And one of Hubble's biggest achievements there is that in an observation of a galaxy called the Whirlpool Galaxy, this pattern in the very center, the nucleus of the galaxy, provided some of the first evidence that there was a supermassive black hole at the center of this galaxy. And by extrapolation, we now know, thanks largely to Hubble, that there are supermassive black holes at the center of almost every galaxy in the universe. And finally, one of the most famous images from Hubble is known as the Hubble Deep Field. This is not that image, but this is an image that is comparably incredible. This is known as the Hubble Ultra Deep Field, which was taken about 10 years after the original 1995 Deep Field image. So essentially, the telescope turned to a blank patch of sky and focused on it for a combined total of 11.5 days. And in that time, the light that it collected revealed over 10,000 galaxies. The galaxies that you see here span between about 1 billion years ago, we are looking back in time by 1 billion years, to almost the end of the observable universe, which means that we're looking back in time to essentially as close to the Big Bang as we can possibly see with these wavelengths of light. So all of that is contained in an area that is only 1/100th of the area of the full moon. And with that, I am going to wrap up my talk and open it up for questions. So I haven't been watching the chat. Josh, do we have any questions that people have
We
dropped
don't
in?
have any questions right now, but feel free to ask anything.
Yeah, if we don't have anything, we could actually jump straight to the activity because it actually blends really well with this. So Avery, our third presenter, has been preparing a bank of resources from Hubble, including a lot of images that go more into detail on some of the stuff that I sort of brushed past here.
Yeah, thanks, Nico. If we were in person, I would ask that everyone sort of give a round of applause, but since we are on YouTube and limited to the internet, we can just jump straight into this. So I'm gonna take the screen away from you. Yeah. So I'm just gonna start by sort of going over a couple images that are fairly typical of what Hubble sort of observes day to day. So first we have a grouping of what appears to be two very close galaxies, actually named NGC 2292 and 2293. And what these are, they're two elliptical galaxies which have become gravitationally bound together and have begun to merge into one final, much larger galaxy. And what Hubble observes here is we can actually see quite a lot of the structure which these galaxies used to have sort of beginning to blend into each other. This type of thing is quite common. And it will come up later when we look back at the Hubble Ultra Deep Field. Here is a typical grand design spiral galaxy, actually named NGC 2525. But there is something special about this galaxy. In the box on the left here, you can see a bright blue light. And this is actually a supernova. Hubble captured this just about a month ago, or 2 months ago, my bad, on October 1st. So this was pretty lucky for Hubble to capture this. And It was a very quick event, and hopefully some good science comes of it. This is a picture of a fairly deep view of space. Something important to note here is that these bright objects are likely stars, which Hubble has captured in the foreground of taking this much wider shot of the universe. And you may notice a pattern sort of towards the center of this image. And this is what's called gravitational lensing. It's a phenomena which occurs when there is a large concentration of mass somewhere, and being observers from a centered point, Hubble, there are certain angles at which the photons from certain objects pass in front of these very massive objects and sort of converge. So what Hubble has captured here is actually an image of a galaxy. You can see that this it's pretty pixelated, but this is actually fairly good resolution for a lensed object. And what you can actually see is there's sort of nodes of light along this arc. If it was complete, it would be called an Einstein ring. Those are very, very, very rare. And unfortunately, we don't have very many pictures of them. But this is a partial Einstein ring. And in total, this is actually one galaxy which has been lensed 12 times around this galaxy cluster here. So lensing is a property of general relativity. We don't need to get into it. But yeah, it's a really cool phenomena, and it really gives us what's important about this is it allows us to see things which are much, much further back in space than what we would typically be able to see. So this galaxy is probably thousands or billions of light years behind this foreground picture that we've taken here. So in a similar vein, here's a picture which Hubble has captured of a similar deep field. And this is actually this very zoomed in portion here. It's the earliest known galaxy that we've ever found at what's called a redshift of 10, which means that the light which we're seeing has been shifted down by about a factor of 10 in terms of energy. At least that's my understanding of it. You can notice in this picture that there are more foreground stars and many, many, many galaxies around here. But the interesting thing is that this galaxy at a redshift of about 10 is actually from within the first 500 million years of the universe. So this galaxy that we're seeing, this light is from 13.3 billion years ago. And this image is actually only 2,500 light years across approximately. That's about a 40th of the size of the Milky Way. So this primordial galaxy is very, very, very small compared to the modern galaxies that we see today, and likely had an insane amount of star formation. But the reason it's very red is because it's very late. And that's something important to think about as we sort of move forward, looking at these other pictures. So here's a very similar picture to 2 pictures ago. And you may notice that there's quite a lot of lensing here. That's very true. There's at least, there's dozens of parts of lensing. You can see this interesting sector here where a galaxy has been essentially smeared in its resolution, which I thought was interesting. But you may notice that there are actually these strange squiggly lines all over. And you may think to yourself, well, that's just more lensing. But actually, these are asteroids, believe it or not. These are things within our own solar system, which Hubble has captured when it's trying to look further out into space. And the reason that they're squiggly like this is purely because of how Hubble sort of orbits the Earth and because of how it captures the images. And these were manually picked out. Another thing with Hubble that we have to sort of keep in mind when we're looking at these pictures is that a lot of them have been they've been clarified. A lot of the noise has been taken out. Some things are false color, especially if it includes ultraviolet or infrared or any of the other wavelengths which Hubble can resolve aside from visible light. So a lot of the things have been doctored up by scientists, by artists, but that's sort of just for the benefit and understanding of the observer. So yeah, I think that's a very interesting picture because it shows us something which is billions and billions of light years away and stuff which is within our own solar system, all in one picture. And going back to the solar system, Hubble, as Nico went over, can also resolve the planets within our own solar system very, very well. So this is a picture which was taken fairly recently, I believe in July, of Saturn. And it was taken on July 4th. So it's sort of NASA's hooray to America, I guess. Yeah, oops. Anyway, yeah, very well resolved image of Saturn. Very cool. And this is a very young object called Eta Carina, which is very, very interesting in that in its shape and how young it is and what is actually contained within it. This was taken last year by Hubble, and it's actually in UV. So this is a false color image. And what it found was that there's magnesium within this gas in this nebula here. So Hubble is continuing, even though it's over 2 decades old, it's continuing to aid us in our understanding of our local neighborhood, because this is within the Milky Way. I think it's fairly close. Yeah, it's only 7,500 light years away. Anyway, very cool image. I urge you to look this object up. There's some weird stuff going on at the center here that we still don't fully understand. Yeah, so sort of on to the main purpose of this activity. And I'll pull up another page here that I have. Oops, that's the wrong thing. Maybe I don't have it.
Setting that up, we do have some questions that we could maybe go over.
Oh, wonderful. Yeah, so this is the ultra deep field that Nico mentioned earlier. There's a link which you can link with a little note which you can download it at. It's very high resolution, composed of many thousands of images. But Josh, if you wanted to sort of bring up those questions, feel free.
Mm-hmm. So Leslie asked back to you, Nico, what's the future for Hubble? Is there any plans for that?
Yeah, so Hubble was not designed to last this long. So we were very lucky to have it 30 years after its 30 years into its 15-year planned lifespan. But the idea of the future of Hubble was there's kind of a hard limit and a soft limit. The soft limit is we expect Hubble to last through the 2020s because we think that all of its parts look reliable enough to do that. In terms of just general reliability, the gyroscopes in Hubble have been giving some worrying signs lately. And so there have been all of these plans that if Hubble needs to go down to just 2 gyroscopes functioning at a time instead of all 3 that it needs, there is a 2 gyroscope mode that's now actually been operating on since 2005 to make sure that its gyroscopes don't get too much wear and tear from overuse. And we can even take it down to a single gyroscope if we absolutely need to, but then we'll be limited at which parts of the sky we can look at. If all of them fail, then Hubble will just be pointing at the same place forever. So we will not really be able to use it anymore after that. So that's the soft limit. As long as all of its parts keep working, we will get to keep using Hubble into the 2030s. And at that point, its orbit is expected to decay from like the slight friction that it has from the Earth's atmosphere. So there will be a time when Hubble is deliberately deorbited, and that will happen about in the 2030s. But we have a good 5 to 15 years of Hubble left, so that's the idea.
And Daniel asked a question, building off of that, is there a proposal for a true Hubble replacement?
So I saw that question. I thought about it, and I think in movie terms, I wouldn't call it a Hubble remake. I would call it a Hubble sequel, because it takes the concept of Hubble as this sort of flagship observatory that sees things that we've never seen before, and goes in a slightly different direction. So the successor to Hubble that we usually consider to be most important is called the James Webb Space Telescope, or JWST. And the idea of that is that it's going to be an infrared telescope, whereas Hubble mostly focused on the optical and ultraviolet wavelengths. So JWST will have a much bigger collecting area. It will be much further away from Earth to avoid the infrared signal of Earth itself, is I believe why. So it won't be in orbit around the Earth. It will actually be between, it'll actually be slightly around the sun from Earth, if that makes sense. So it'll be at a point that is constantly trailing Earth's orbit, and that is many, many, many times further away than Hubble is. We'll never be able to send people there to do maintenance, for example. And finally, it is going to focus, like I said, on different frequencies. So the idea of JWST is that it's going to peer further into the universe and further back in time than Hubble was able to, and it's going to answer some questions that Hubble could not. In terms of remaking Hubble, something like it, we're not, as far as I know, there are no plans to make another sort of space optical and ultraviolet telescope like this. But that may change after Hubble fails, because right now we rely on Hubble very heavily still as astronomers.
So going a little out of order here, but this kind of builds off of what you were saying. What does deorbiting look like? Marta wants to know.
I wish I knew this better. If we do nothing, what I read is that Hubble will just gradually slow down a little bit and get lower and lower in the atmosphere until it's sort of going through enough air that friction with the air slows it down sort of catastrophically. And then it will do that classic thing that meteors do, where they catch fire and they fall to Earth. So it will mostly burn up in the atmosphere, is my understanding. It's a planned operation, so NASA may actually be helping it along when that happens and making sure that it burns up in the atmosphere in a place that will do no damage to somewhere on Earth. So making sure it happens, for example, over a large body of water. This is sort of me taking an educated guess. I'm not 100% sure about that. So if either of you can fill in the gaps, I'd appreciate it. But that's the extent of what I know.
Well, I mean, with the eccentricity of the current space-oriented billionaires, who knows? One of them might decide to save it, keep it from deorbiting. Who knows?
Yeah, so I guess only time will tell for that one. So another question. You were mentioning that Hubble is getting to the first and best images of its time. Can anything on Earth ever come close, even with our modern technology?
So amazingly, we are making some strides in technology that beat the limit that I was talking about, where I called some images the best that we can get from Earth. One of them is called adaptive optics. And the idea is that telescopes on Earth can shoot a laser into the atmosphere, measure that laser's sort of wobble with a camera, and then figure out exactly what the atmosphere is doing to warp that laser's path. And there are tiny devices on the telescope itself that make micro adjustments to the mirror on scales of microseconds, as I understand it. And on scales of milliseconds, very quickly. So they very rapidly adjust the curvature of the telescope's mirror or the telescope's optics to make sure that whatever the atmosphere is doing, the telescope does the opposite. So essentially that can sharpen your images, because instead of having light scattering all over the place because of air differences in the air, you exactly counteract that. And you artificially focus the light by changing the telescope's optics in real time. It's incredible as a piece of technology, and there are still technologies coming online that are actually better than that. So that currently can't beat Hubble, but there are some sort of newer technologies that I admittedly understand very little about that supposedly can reach the same resolution as Hubble or very close to it from the ground. That's something that we did not expect when we launched Hubble, but it's one of the most exciting things about astronomy today.
All right, so some more questions. We're moving more into Avery's territory. So how long will it take for those two elliptical galaxies to merge? So I don't know if you want to go back to those two. Yeah.
I haven't specifically done any research exactly about it, but it will take probably on the order of hundreds of millions to billions of years for them to completely merge. I would err on the side of hundreds of millions. This specific galaxy is 120 million light years away. So who knows? It could have already merged, but the light has yet to reach us. What we can expect to see is probably a much larger galaxy with a probably fairly similar profile. So over the size of the galaxy, you have a certain density profile of the light, which we see. It'll probably be pretty similar, as most ellipticals are fairly uniform in their shape, that being either fairly spherical or like pretty uniformly ovular in nature. Yeah, I mean, depending on what you look for in a galaxy, it will probably be pretty boring just to look at. But in terms of what actually has happened in its past and what might happen in its future, it's actually fairly interesting. A thing to note about ellipticals is that so ellipticals are thought to appear from mergers of multiple galaxies over their lifetimes. And an interesting thing about ellipticals is that they tend to not have any star formation within them. Very little compared to, well, they might have some, but very little compared to spirals. So any of the stars which are burning, they're going to be sort of what lives out the rest of that elliptical's lifetime with it. So just an interesting tidbit there.
All right, another question, which is a pretty good one. Avery, you touched on it a little bit, but how much modern image processing enhanced what Hubble is getting in?
Oh man, I would, compared to ground telescopes, I would say it's probably a lot less. Nico might know more about this. I personally don't really know the intricacies of actually processing raw astronomical data. Yeah, sorry. I guess I can't really answer that directly. I could
think
defer
I'll
to-
jump in with what little I know, if that's okay, because I don't know the details of it. It's possible that there have been some advancements, but I think the goal with a good telescope is that if you build it well enough, there should be a really standard way of processing its images, and then you shouldn't have to do much else. So there are technologies like the adaptive optics, like the laser into the sky technique, that are built into the telescope. But in terms of image processing, I think the goal with most of these telescopes is that we should have to do as little as possible. And if you have to do a lot, something has gone wrong. So I think image processing has gotten a lot better. The images that we look at in papers now look a lot prettier because we know how to process them for the human eye better. But the scientific data that they carry is still about the same.
Yeah, touching on that a little bit. Some of these like big, like specifically this image is composed of thousands and thousands of Hubble's like exposures. So this is not just like one image that Hubble sort of took on a whim and they said, we're going to zoom in super far and see what we can see. But this is actually a composite picture of multiple like thousands of images stitched together. And that's why we can get such good resolution. So yeah, I mean, that's part of it as well. The more images we can get of an object, as Nico said, from the ground compared to, say, your backyard telescope, that really helps in terms of the quality of an image as well.
All right, yeah, and Susan looks like in the chat was able to confirm what Nico was saying about deorbiting, and Mardo wants to know if we'll be able to watch its last images. I guess that's another thing of only time will tell. I mean, that would be pretty cool if we could. As Avery was saying earlier, I guess the billionaires might have a little bit of a say in that. But yeah, so another question. Is the Whirlpool Galaxy thought to have a black hole because it's a cuspy profile, or is it something about the shape of the cross inside the bright spot? So if we want to go back to that picture.
Yeah, sure. I can quickly share my screen, actually. Let's see how quickly I can work Zoom. 5 more seconds. And done. So can you guys see my screen?
Sorry, yep.
All right, so I'll quickly go back to that picture. After all that, the really unfortunate answer is I'm not 100% sure. So I looked this up a little bit before the talk, and I'll for purposes of full disclosure, this is partly based on my research just today, based on putting this image into this talk. But my understanding is that analysis of what that cross is includes a model of an accretion disk around that black hole. So the reason that light is blocked is because matter is swirling around it very quickly in a way that looks a lot like a disk, like a flattened out object, rather than just as like a blob of matter that's sort of amorphous. I'm assuming that in order to make that work, in order to explain the fact that there was a cross there at all, astronomers had to create a model that said there has to be a huge gravitational potential there concentrated into a single point. And the only thing that can do that is, or the necessary thing that would form at a point with that much gravity, is a supermassive black hole. So it matches what we'd expect to see from a black hole, and I guess it kind of rejects any model that we can make that does not include a black hole. That's the extent of my knowledge, but it's considered to be one of the pictures that confirmed that there were black holes at the center of galaxies in general.
Yeah, just to sort of jump onto that, a lot of the confirmation of this was done in X-rays. So we can see that there are super energetic jets of gas emitting X-rays coming from the center of what is this, M36 or something? I can't remember exactly, but M51, yeah.
Right.
Yeah. So that's part of it. That's part of the reason that we can sort of theorize that there's a black hole in there.
All right, and another question that's pretty relevant to our Astronomy 1001 classes this week at the University of Minnesota. Has Hubble been important to understanding dark matter?
So I'll do my best to take this one because I can't think of a specific experiment that Hubble did best or that Hubble was necessary for that told us that there was dark matter in the universe. I am positive that somebody has taken some observation with Hubble that has sort of clarified the amount of dark matter in a certain galaxy. But the signals that we look for dark matter, because there are a few, are how quickly do galaxies orbit around clusters, like the center of large clusters of galaxies? How quickly do stars orbit around galaxies? And in X-ray data, actually, specifically, what's the energy of the gas that's in the middle of large clusters of galaxies? And all of those questions are basically posing the same thing, which is when you have a bunch of stuff in the same place, how much stuff actually is it? And we can probe that by seeing what the effect of gravity is on the matter around it. Hubble is not very good at any of those things. So I think in terms of dark matter, it's not a super useful telescope. There are mostly other telescopes that have filled in those gaps. There are major parts of our understanding of the universe that I did not touch on at all that Hubble did help us with. One of them being dark energy, which is totally different than dark matter. But just to leave that thread hanging if anyone's curious. So
a little bit more about the dark matter side of Hubble is another way we can see dark matter, observe it, is through lensing. And I believe that a lot of the way Hubble's taken a lot of these pictures, and Avery even showed some that showed lensing, and we can measure the diffraction of the lensing, and sometimes we can measure more mass than we can actually see, and that could be evidence of dark matter.
I'd like to amend my answer. That was absolutely correct. Hubble has helped us a huge amount because it's found a lot of gravitational lenses. So thank you, Josh.
All right. Another question, do all galaxies swirl in the same directions?
I'm going to say no. And the reason is that there is no preferred direction to space at all. So galaxies are just as likely to form like right side up or swirling this way as upside down, and therefore swirling the other way. So that's the main issue, is that there is no preferred direction that they have at all.
It's an interesting question. I like that. All right. That's
it was very cool.
Questions I can see right now. Maybe we can head into back to the activity, the ultra deep field.
Yeah, so I think we're pretty much almost out of time, but one thing that I did want to point out with the deep field is that given how broad of a survey it sort of is, you can sort of see almost every single instance of the things that I touched on earlier. So you can see lensing, you can see very, very old objects, you can see you can maybe see supernova. I can't exactly talk to the validity of that. And you can definitely see mergers. And you can see all of those different types of galaxies as well. So for example, maybe one of the most prominent galaxies within the ultra deep field is this galaxy, which is actually named after the ultra deep field, called UDF 423. And it's a fairly large as Nico would call, clumpy grand design spiral, which is because, so the ultra deep field was taken at such a redshift that all of these images are very, very early on in the history of the universe. I can't remember exactly how far back it was.
I think there's a really wide range, which we'll just put out there, but many of these are older than 7 billion years.
Very true. Very true. Yeah, and this galaxy, it just as an example, it is something similar to what we observed earlier in the talk. And you can see that this type of galaxy is likely an elliptical. You can see high redshift objects, which could possibly be galaxies forming earlier on in the universe than any of these other ones as well. So I just urge you, given the breadth of how huge this image is and how wide of an area it observes, to just sort of explore, to just sort of look around, see what you can see. When we were looking before this talk started, we thought we could spot a couple instances of lensing. So maybe be on the lookout for that if you do choose to download it and take a look around. Another interesting thing is you can see these sort of green galaxies. I believe they're called P-body galaxies or something. I can't exactly remember what they're called. But they're sort of they're a very interesting object that a lot of research is being done on at the moment.
Yeah, I think my lab is one of the ones doing that research, which is exciting. Not me personally, but they're called green P galaxies.
Green P.
I was curious.
I was close.
Yeah, you were actually. So I like P-body too.
Yeah, and definitely maybe here's a merger here. You can sort of see this tail, or maybe that's lensing. Who knows? It's a very interesting image to explore. And given you can continue to zoom and zoom and zoom, it's very, very fun to just sort of screw around for hours on end looking at it. Maybe that's a bit of an exaggeration, or maybe I'm just a little bit of a space fanatic, as Josh would say. So yeah, that was pretty much all I had. Oh, well, there are a couple websites that I linked that are pretty cool. This is a website of what Hubble's looking at the moment. Right now, it's focused on a couple of massive stars for Dr. Andreas Sander. I don't exactly know what kind of research he's doing, but I think it had to do with Wolf-Rayet and supermassive red stars. And here's a sort of quirky website. What did Hubble see on your birthday? So for example, if your birthday was on November 24th, in 2013, it was looking at this pretty awesome galaxy cluster with a lot of seemingly blue shifted objects, a lot of lensing going on maybe. Anyway, just a cool little thing. Most of these are through NASA or NASA affiliated things. So yeah, huge thanks to them. All of the images are credited to NASA or some astronomer associated with NASA. So yeah, that's pretty much all I had when it comes to the activity. If there are any more questions, feel free to send them in the chat.
All right, thank you, Avery. We do have one question right here, which I think is a pretty good one. Has Hubble offered any evidence to reduce any current margin of error in the Hubble constant?
Oh. So this is what I'm particularly interested in, is the H0 tension, the Hubble parameter tension. We don't actually know if it's a constant or not. It could have varied over the time of the universe and could be varying right now. It's really dependent on if the universe is accelerating in its expansion or not. I can't exactly speak to what research has specifically been done using Hubble Space Telescope data, but we can use lensing as a way to estimate the Hubble parameter. And that's sort of actually related to what I'm doing in terms of research at the moment. So if you have a lensed object, specifically, say we had supernova lenses are very, very rare. But if Hubble was able to capture, I was trying to go to the supernova picture that I had. So if we were able to capture an image of this supernova, and it just happened to be lensed like this. So say we had an image here. I'm just going to annotate this actually. Sorry, I'm sort of taking over, but since we're over time, I figured it's fine. Say we have an image here, an image here, an image here, and an image here. These are all going to arrive at different times. And if we can determine when they arrive, so say this one arrives first, this one arrives second, that's not technically right. This one arrives third and this one arrives fourth. If we can determine the difference in time between these, then we can, and the redshift which it experiences, we can try to determine H naught. So Hubble doesn't necessarily have the best resolution when it comes to this. Some recent papers which have been put out, actually, I guess I can speak to this directly. But some recent papers which have been put out use adaptive optics in addition to what Hubble uses. So they use images from multiple telescopes and sort of coincident them together and use that data to sort of try and extract this change in time. So yeah, sort of it hasn't really helped much in terms of actually narrowing it down, but we are getting more and more points of information from it. Because that's sort of the key. We want to try all avenues in order to narrow where this tension is coming from. And just for fun, 63 is about 63 is what Planck, I'm just gonna not do that, is what Planck has estimated. That's sort of close to what Roger is quoting at 45, and or maybe it's 68. Anyway,
I think it's 68. They're around 70.
Yeah. And then the quoted one from a researcher named Adam Rees, who does what's called distance ladder measurements of this, purely based on type 1a supernova observations, which aren't lensed, just observing them and calibrating them with what's called Cepheid stars, which are, they vary so we can determine how far away they are. And then since we think we know what energy is output by the type 1a supernovas almost exactly, because they're theoretically very consistent in when they happen, he tries to determine the redshift based on their distance. And from that, he tries to extract a value for H naught. And he's consistently come up with a value, him and his team have consistently come up with a value around low 70s. And there have been independent verifications of this type of thing using different wavelengths, different methods. So there is this tension that still exists. So yeah, sorry, that was a tangent.
That was an awesomely thorough answer, actually. A lot of that was new information to me, so that was really interesting. I was going to jump in with a very short addition to this answer, which is that Hubble, the way that Roger phrased that question was really interesting because the current margin of error on the Hubble constant, Hubble actually is the error on the Hubble constant. The Hubble telescope was one of the first devices that ever tried to estimate it. And its observations of supernova 1A and of Cepheid variable stars were some of the things that went into those estimates. So that number 73 kilometers per second per megaparsec, that comes from Hubble observations. That's actually one of the places that it's derived. And then there are these other estimates from other things that have totally different numbers. So that's why the tension exists, is Hubble versus other telescopes.
Yeah, and the sad part is their error bars don't overlap. So in a lot of cases.
Or the really cool part, depending on which
or the very cool part, yeah.
Because that might mean there's something really interesting going on.
Yeah, Roger, I guess we don't really know. It really just depends on if there is an energy limit to the universe, because if the energy density of dark energy does, it won't happen. It probably, as an undergraduate, taking a colloquial guess, the big crunch won't happen before all the stars burn out. So I wouldn't worry about it.
All right.
I think the short answer is sorry, I think the short answer is no. I don't think we know yet, and we're trying to pin it down. There's some evidence that it might be closed. There's some evidence that the universe might be geometrically flat, and that it will just keep expanding forever. So we're working on it.
Okay, I think that's all we have. I really appreciate the discussion that we had in the chat. A lot of great questions. Yeah, so thank you all for coming, everyone. And if Nico or Avery don't have anything else, I think we'll be signing off.
That sounds good to me.
Thanks, everyone. Hope you tune in next time. I don't know when the next one is.
Our next one, I think, is in 2 weeks. So on the 16th, and we'll be talking about the first 20 minutes of the universe in 20 minutes. So if you're still watching, hopefully you are interested enough in astronomy that you will tune in. It sounds like a really interesting topic. And with that, I will stop the live stream from my end. So have a great night.